Hi everybody. Today we're going to be talking about forces. A force is the action of one body on another, and it tends to move a body in the direction of its action. For example, if we look at someone pushing a shopping cart, they're applying a force to the shopping cart to move it forward, and the cart moves in the direction that we push it. Note that force is a vector because it has both magnitude and direction. So Newton's first law of motion is also sometimes called the law of inertia. So let's look at the first part. It says a particle remains at rest if there is no unbalanced force acting on it. Let's take the example of a ball. If we had this ball sitting on the ground, and if there was no wind and nothing went near the ball and it was at rest, this ball is not going to suddenly start moving on its own. So that is what they mean by a particle remains at rest if there is no unbalanced force acting on it. Now the second part of the law says that a particle continues to move uniform velocity if there is no unbalanced force acting on it. So uniform means same. That means if a particle is moving with some velocity, which means it's moving with some speed and in a certain direction, it's not going to change its speed or its direction if there is no external force making it do so. Let's look at a ball that's already rolling because somebody kicked it. If this ball followed the first law, then it should just keep moving forever, right? Say it's moving at 5 kilometers per hour east with that constant velocity. But we know that eventually, regardless of whether it hits anything, this ball is going to come to a stop all on its own. It's not just going to keep rolling forever in a straight line, right? And why is this? Because if Newton's first law were true, wouldn't the ball keep rolling forever? And the answer to this is yes, it would. Now, if we dropped an object in space, that object would continue to move with the uniform velocity in a straight line, and it would not stop because there are no other forces acting on it. However, on Earth, we have forces like air resistance and friction and gravity and other forces that will change the velocity of your object even if they are not directly touching the object. So why did this ball stop? Well, there's a force we haven't discussed yet, and it's called friction. So the ground that the ball is rolling over is usually not like flat surface. It usually will have grass and rocks and things that make it bumpy. When the ball is rolling over a bumpy surface, it causes friction. We have a force of friction slowing down our ball in the opposite direction to its motion. So this causes the forces to become unbalanced. And the ball will not continue to move with uniform velocity, and it will eventually stop. Now let's talk about Newton's second law of motion. This law states that the acceleration of a particle is proportional to the vector sum of forces acting on it and is in the direction of this vector sum. From this law comes a very important equation that you'll see used very often in the forces unit. This equation is F equals ma, where F is the force that you applied to an object. M is the mass of the object that you apply the force on, and A is the acceleration of the object caused by that force. Note that acceleration equals 0 if you have uniform velocity, meaning your initial velocity and your final velocity are the same. That means that your object has not accelerated between those 2 points. Or if your object is at rest. If your object is not moving, there is no acceleration. Now let's talk about the units. Force is measured in newtons. A newton is a kilogram meter per second squared. Mass needs to be measured in kilograms so it can match up with the units of a newton. And acceleration needs to be in meters per second squared, so it can also match up with the units of a newton. Note that the law states the acceleration of the particle is proportional to the vector sum of forces acting on it. The sum of forces has this little weird looking E, which means sum. That means that if I have an object, I have to calculate all of the total forces acting on it and sum them up, and that will equal the object's mass times its acceleration. Newton's third law of motion states that the forces of action and reaction between interacting bodies are equal in magnitude, opposite in direction, and collinear. They lie on the same line. So let's look at an example. If I push on this wall with 10 newtons of force, the wall will push back on me with 10 newtons of force. So these forces have the same magnitude of 10 newtons. They have opposite directions, and they're collinear, meaning they lie on the same straight line, just opposite in direction. Now let's take a look at this example. When you are sitting in a chair, the force of gravity is pulling you down. At the same time, the normal force is pushing you up. Both of these forces lie on the same straight line and are opposite in direction to one another. They also will have the same magnitude. The amount of newtons that you are being pulled down by from gravity are the same amount of newtons that you are being pushed up by from the normal force. Now let's talk about the three fundamental dimensions of physics. Fundamental dimensions are units that cannot be broken down any further. So for example, when we talk about speed, the unit of speed is usually kilometers per hour, for example, if you were on the highway. Why did we not put kilometers per hour as one of our fundamental dimensions? Well, kilometers is a unit of length, and hours is a unit of time. So speed can be written as any unit of length per time. For example, we could have written speed in miles per hour, which is still a length over a time unit. We could have written it as meters per second, which is still a length divided by time. Could have been meters per minute. It could have been kilometers per day, or even miles per year. So speed can be written as anything that is length divided by time. Almost every unit that you will run across is going to be a combination of the three fundamental dimensions. For example, when we talk about newtons, which we use to measure force, 1 newton is a kilogram meter per second squared. If we were to convert this into its fundamental dimensions, kilograms is a mass, times meters, which is a length, divided by seconds squared, which is time. Newtons are in mass times length per time squared units. Now let's talk about the different types of forces that we have. Forces can be classified into two main groups. So there are contact forces, and these are the forces that we're going to be dealing with. Contact forces are forces which cause an object to move because you're directly applying a force by touching the object. Then we have action at a distance, or body forces. These forces are those which exert a force on an object without actually coming into contact with it, like gravitational force, which keeps our planets together in space, or electric force or magnetic force. So most of the forces that I'm going to be talking about today are contact forces. So let's talk about the different types of forces before we get into drawing free body diagrams. The first force we're going to be talking about is Fg. Now, when we denote forces, we use a capital letter F and a little subscript to indicate which force we're talking about. Here I have a capital F with a little g, which means force of gravity. Force of gravity is also sometimes known as your weight. Note that your weight does not equal your mass. Weight is actually the force of gravity, and to calculate that, we take the mass of the object in kilograms and multiply it by the gravitational acceleration constant, g, which is 9.8 meters per second squared. So your weight is equal to your mass times your gravity, whereas your mass does not take gravity into account. Note that force of gravity always points downward. So say we have a box on an incline here. Gravity is always going to be pointing downward regardless of what direction the other forces are pointing in. If we have a box sitting on this flat plane, the force of gravity still points downward. If we have a person in a boat, the force of gravity still points downward. Now the rest of the forces we're going to be talking about are all contact forces. The first force that we will talk about is the applied force, Fa. This force usually arises whenever someone is physically pushing something with their hands. So if I have a crate and I'm pushing it with my hands in that direction, there is an applied force to the right because I'm pushing it towards the right. Next, we have a force of friction, F. There are two different types of frictions. You might see force of friction with a little s, or force of friction with a little subscript k. F with subscript fs is the force of static friction, and F with the subscript fk is the force of kinetic friction. Static friction is used when an object is not moving, so its velocity equals 0. Sometimes you might see the force of friction static max. So when something is at rest and we're applying a force on it, we need to make sure that we're pushing it harder than the force of friction that keeps it in place. Otherwise, it's not going to move. When we push with a certain amount of force, the amount of force that you have to push with to get your box to just start moving, that is the maximum force of static friction. Then once your box is moving, when your velocity does not equal 0, that is when you will use kinetic friction. The equations to find static and kinetic friction are almost the same. The equation to find friction is the normal force, which we will talk about later, times mu, which is a Greek letter, kind of looks like a U. Now this can be either mu k or it can be mu s, depending on if you're looking for static friction or kinetic friction, which depends on if your object is moving or not. Usually in a question, you will only have to be dealing with one type of friction. Either your box is moving or it's not moving during the period that you're trying to find the force of friction for. So these are the coefficients of friction. Note that for some forces, there are equations that you can use to find them, such as the force of gravity, which we talked about earlier, and the force of friction. Now, if we look at this box, force of friction is going to be pointing that way. The direction of the force is always opposing motion. We will see this more in free body diagrams when we try to put all our forces together. Now we're going to cover force of tension. So force of tension is similar to the applied force. There's no equation to find it. Usually arises when you're pulling a box that has a string or a rope attached to it. Instead of making contact with your hands as we would in applied force, the force of tension is when we make contact with our object and a rope, a pulley, a string, anything like that. If we have a box hanging from the ceiling, the force of tension is going up because the box is being held by the string. If the string were cut, the box would fall down. So the string is the only thing holding it up right now to the ceiling, and so the force of tension will go in that direction. The next force we're going to talk about is the normal force. The normal force also doesn't have any equation for it. However, it always acts perpendicular to a surface. For example, say I have this box. Our surface runs left and right. So if we had to make a coordinate grid, this surface runs in our x direction. Normal force is always perpendicular to the surface, so we know that the direction it must go in has to be up or down, so it can be 90 degrees to our surface. The force of gravity always points down, so the normal force is always perpendicular to the surface but in the other direction, so our normal force points up. Sometimes people think of the normal force as always opposing gravity. That's not always the case. Say we had a box on an incline. However, our surface is now tilted, which means if we made a coordinate grid, it would also be tilted. This would be our x-axis, and this would be our y-axis. Because gravity is pointing straight down, our normal force always goes upwards away from the surface and perpendicular to it. Now there's 3 more forces that I'm going to go through. The first one is Fd, buoyant force. Buoyant force is similar to normal force when you're in the water. So say we have a boat in the water. If this boat was sitting on a level surface, like on the beach, the normal force from the earth would be exerting an upward force on the boat. However, because we're in water, this force is now called the buoyant force. And it does the same thing that the normal force does. It exerts an upward force from the surface, which is now our water. Next, we have spring force. So if we have a spring, like a slinky, and we stretched it or we compressed it, that spring would automatically try to go back to its equilibrium position where it was not stretched or not compressed. Sometimes you might see spring force called restoring force. K is the spring constant. Spring constant is a constant depending on the type of spring that you're using. Every spring has its own spring constant. X is the displacement of the spring. It can be positive or negative depending on if you stretched or compressed your spring. Now let's talk about the drag force. So imagine you jumped out of an airplane. As you're rushing towards the ground, you will feel a lot of wind slowing you down. That wind is basically friction, but in the air. And when it's in the air, it's called a drag force. So those were all of the different types of forces that you should know in order to begin drawing free body diagrams. Now let's do some examples where we look at the different forces at play on an object and draw free body diagrams. which are commonly known as FVDs. In the first example, say we have a man pushing a box. Note that if there is no friction, the question will usually tell you. If it does not mention anything about friction, then include friction in your free body diagram. If a man pushes a box, we can assume that he might be just pushing the box from here with his hands. The first thing I do is to just draw a picture so I can see what's going on. If we were to draw the free body diagram, the first thing we do is to draw a box. It doesn't matter whether the forces are applied to a person or a car or any other object, we will just draw a box. So usually we follow a general coordinate grid, which you can change as well, but this is the most common notation. This side is the positive x-axis and this side is the negative x. Up here is the positive y and down here is the negative y. So now if we look at this person pushing a box, he's pushing it in the positive y direction. It's easier to just assume that when you have an applied force, it's going from left to right, unless otherwise stated. This is the force that we can clearly see. However, there are forces that we cannot see in the picture, but we know they exist because we went through all the different types of forces earlier. Anytime you have an object moving on a surface, you would always have a force of friction opposing the direction of motion. So our box is supposedly moving to the right, which means friction should be slowing it down, and it would be pointing in the opposite direction. And it says the man is pushing the box. It doesn't say the box is at rest. So it should be the force of kinetic friction, FFK. These are forces in the x direction. When we talk about forces, they can have different components. There can be forces in the x direction, forces in the y direction, and forces that are on a diagonal and they end up being in both planes. The next force that we have is going to be force of gravity. Every single object has a force of gravity pointing directly downwards, and we have a normal force. Anytime you have an object resting on a surface and it's not just being held up in the air by a rope or a pulley, you would have a normal force that is perpendicular to the surface. These would be the forces that are acting on this box. We may also have forces on an angle, as I mentioned earlier. Say I push the box like this. So the way that we would draw that force is on an angle like this. It's an applied force. Let's continue on to an easier example where we have force of tension. Say we have a box hanging from the ceiling. What forces are at play on this box? Well, the first thing I do is I draw a little box. Remember that gravity always points downwards. We don't have friction because we are not resting on a surface, we're hanging from the ceiling. We don't have a normal force because, again, we're not resting on a surface. We don't have any buoyant force because we're not in the water. We don't have a spring force because we don't have any springs in this question. We don't have an applied force because nobody is pushing our box. The only other force we have is a force of tension because what's holding the box up to the ceiling? It's a rope. So this is a force of tension. So there are 2 forces in our y direction and 0 forces in our x direction. If you have any questions, leave them in the comments below. And for more information related to this topic, visit thestemtutor.org. Bye for now.